In this lesson, we're going to focus our attention on introducing appropriate techniques, technologies, and software associated with computer networks. And so let's first consider what we mean by a network. And we can think of a network as being a computer connected to various resources or devices that allow for communication. And so once a computer is connected to a network, it is called a host. And we make use of network interface cards that allow for the establishment of these different networks. And so let's get into more detail about what we mean when we say a network. And we have all of these multiple devices that are connected, and the devices can be a desktop, a laptop, tablet, or other mobile device, and now even can be cars or automobiles. And so we have a big collection of interconnected networks that all make use of protocols to communicate, hence the internet. And so let's kind of consider what we mean when we say what is the internet. Well, you want to consider an example of a postal system. And so let's say in this example that we have someone that is going to send a letter. And so this young lady can send the letter to her parents or grandparents that live around the world or even across the country. And when the letter is sent, the first thing that needs to happen before the letter can be put in process to be delivered is that the sender needs to provide for the address on the envelope. And so once that is done, the sender will place the address in the mailbox. The mail person will pick up the letter, and then after a little bit of time, the recipient will receive the letter that has been broadcasted or sent around the world or across the country. And so in this case, what we've seen is that the post office has served as a mechanism for transmitting the letter around the world. And so another application of this is, let's consider sending email. Let's say we have someone named Joe that wants to send an email to his grandmother or family that is around the world or on the other side of the country from him. In order for the email to be transmitted, the user needs to have internet connectivity, and this is going to be done via cable modem, or even could be through a cell phone hotspot. But whatever device is being used will need to connect to the internet service provider and so forth. And then appropriate technologies are used in order to transmit the email across the network. And these technologies can include the protocols and processes provided by the internet service provider. And there are going to be specific limitations, such as the size of the email, the speed of the user's connection that will determine the exact time that the exact time that it will take for the email to be received by the recipient. At a high level, this normally occurs in seconds, but at a microscopic level, there are a number of different protocols and transmissions that occur. So if the user sends the email from Atlanta, it has to access the network via modem or Wi-Fi. The email is routed to a regional ISP, which then goes to a core network, and then to another regional ISP close to the city, close to the recipients, and then to a access network as well. And so that basically provides a high-level overview of how mail or email is sent now versus using the post office to send mail. But there's a lot of commonality that is within both of those approaches. So what do these two approaches have in common? Well, the first thing that they have in common is that they have universally understood addresses. And so we have a country and a postal code that is used. And so the staff at if the sender is in Atlanta, the staff at the Atlanta Regional Post Office might not have an idea where exactly the letter is going to go, but they know how to get the mail to India and how to deliver the mail for the postal code of that state. And so they're able to make appropriate changes to process it as needed to that regional center so that it can be sent to the recipient's home. And so in the case of our email journey, we have an IP address that is used. And the routers at the ISP might not have an idea exactly where the recipient is located in California, but they know how to get the packets to the internet core. And so the internet core does know which ISP services the ISP addresses in the recipient's domain. So the message goes to the mail server at the ISP, and it waits for the recipient to dial up her internet connection to receive that email. And so the key takeaway here is that no individual needs to know where all the addresses are located, but with each hop, they know where to forward an item to get it a hop closer. And so now let's dive in a little bit deeper when we want to consider appropriate IP connections that can occur for the transmission of electronic data. So when we think about IP network connections, you want to consider that we have our processors, and then we have our protocol stack that's being utilized, and then we have appropriate packets that can be sent as well. And so you want to keep in mind that the protocol stacks are in the host and they're not in the middle of the network. And so this is important because the operating system will be utilized to address and incorporate the protocol stack. And so once using the protocol stack, we're able to send messages. We can transport it across the network, and then the message, once transmitted, can be reconstructed once it has reached the recipient. And so in this case, we can envision that we're transmitting a message between P1 and P2 that are on two different hosts. And so there are two different ways in which we are able to provide for the mechanisms to implement our network. And we can use that with the internet via Datagram or ATM using virtual circuits. And so with the datagram, we focus on data exchange among computers. And so this is an elastic service, so there's no strict timing requirements. And we have to consider that there are many different link types, and these different link types are going to have different characteristics, but uniform service can be difficult because of that. And we'll have smart end computer systems. That means that they can adapt and perform control and error recovery. And the key description for the internet is it's in simplicity inside the network layer, but complex at the edge. And so when we consider virtual circuits for ATM, we can consider that it evolved from telephone protocols. And so it focuses on human conversation, which enables strict timing and reliability requirements. And it also ensures a need for guaranteed service. And so some of the end components might be a little bit clunky, such as the telephones that are typically associated with it. And so when we consider this, we have to consider that the virtual connection and the virtual channel can result in some complexity inside the network layer, but it results in simplicity at the edge. And so let's consider what exactly does an IP need a protocol stack? Why exactly is that needed? Well, there are a number of factors or problems that we have to take into consideration. Those problems include we'll have arbitrary message sizes, out of order delivery, packet loss, bit errors, and as well as queuing delays. So these are some problems that we have to account for within our protocol stack. So let's take a look at a typical internet protocol stack and how it is composed. And so the IP stack has 5 layers that are associated with it. And the idea of this protocol stack is that we want to ensure the reliable transport of messages from source to destination. And so this allows for efficient communication of data, but it can also result in some hurdles. And so what we will do is we'll focus our attention on each one of these layers and how they help to deliver messages across a physical network. And so the OSI model is another form of our communication model, and you could think of it like a relational database model. We use it for studying networks, but it doesn't have the exact performance that we need in real life. So it's used more as a conceptual framework that we make use of to describe a working networking system. And so essentially our OSI model is going to characterize how our computing devices will function on a network. It provides for appropriate rules and requirements that we need in order to provide for interoperability between our network and software and our hosts. And so you'll see that unlike the IP model, we have 7 layers in our OSI model. And so we have a physical layer, a data link layer, network layer, transport layer, a session layer, presentation layer, and application layer. And so we have our TCP and UDP bundle. Our TCP and UDP protocols are in our session and transport layer. Our IP is in our network layer. Our ARP is in the data link and network layer. Our Ethernet is in the data link layer as well. And so one way to remember each of the layers associated with the IS with the OSI model is a acronym that goes, please do not throw salami pizza away. That'll enable you to remember each layer from the bottom up. So let's first, as we examine each of the available layers that can be utilized, we can start by focusing our attention on the transport layer. And so transport, of course, relates to how we're able to physically move data across the network from one source to a destination host. And so with this layer, we need to be responsible for the transmission of bits in a packet from one host to the next. And what we need to also focus on is making use of our physical systems to interact with our distinct layer protocols as well. And so in this case, we have the transmission of packets from one host across a Ethernet to a hop, which is going to be a regional ISP, to another hop, and then to our host, or to our recipient. And so as we dig down into our transport session protocol, we're going to talk about a few protocol types that are used in order to allow for efficient transmission. We're going to focus on the stop and wait protocol, pipeline transmission, and reliable pipeline transmission. And so let's consider a question. And this question is, who invented the internet? Was it A, Vannevar Bush, B, George W. Bush, C, George H.W. Bush, E, J.C.R. Licklider, or F, Robert Kahn and Vinton Cerf? And so some hints, it's going to be a famous scientist, but think the Manhattan Project. And so the first few choices are all politicians, but they did provide some credit. So J.C.R. Licklider provided the packet switch networking in 1965. Or did not, but that was part of the approach to creating the internet. And then the IP suite to unify various networks was devised in 1973. But the scientists that are deemed the fathers of the internet are Robert Kahn and Vinton Cerf. So one transport protocol that the first transport protocol that we'll focus our attention on is the stop and wait protocol that is used to send a packet across to the network to another host and then we want to wait for a positive acknowledgement. And the acknowledgement is referred as a ACK to represent the acknowledgement. So once the packet is received, we want the recipient to confirm that it's been received and then provide an acknowledgement for that packet. And essentially within that acknowledgement, we're going to look for being able to discern that the packet was received correctly. And so there are specific sequences that are used to denote the signature for packets, and all that we need to know in the acknowledgement is the sequence number of the received packet. And so once that is received by the original sender, then we know that the packet has successfully reached its destination. And so in waiting for the acknowledgement, the sender is going to have a period of time called a timeout. And during this period is when the sender is waiting for the acknowledgement. If the timeout period passes and there isn't an acknowledgement sent, then there is going to be a need for a retransmission of the packet. And so also the destination may retransmit the acknowledgement if it receives the same package again, because the packet could also be lost and the acknowledgement also could be lost. And so one important concept that we have to keep in mind is latency. And latency is the time delay that we have between sending a packet and receiving a packet. So it's basically going to going to be denoted as a measure of delay. And it essentially accounts for the time it takes for data to get across a network. And of course, the latency is going to be different based off of the locations of the sender and the location of the receiver. Someone that is 500 miles away from the sender is going to have a lower latency than someone that is 5,000 miles away from a sender. So but it's not just different distance also. It could be connection speeds between not only the host and between not only the sender and the receiver, but also the networks that are interconnected as well. And so if you want to think about latency in terms of some of the various networks, we can typically denote that the latency to transmit a packet varies for different type of networks. If you have a satellite type of network, it's going to be 800 milliseconds. 3G cellular networks are 120 milliseconds. 4G cellular networks or 4G wide area networks are going to be 60 milliseconds. And so it can vary for the different types of networks that are being used. And so when we compare it with the latency of the latest technologies such as 5G latency can be around 5 milliseconds to 1 milliseconds. And so we can also define a round trip that occurs between sender and receiver. And a round trip time is what we refer to as RTT. And this is going to be the time taken for a small message that we want to send from the sender to the receiver and back again. And so essentially we'll use the round trip time to serve as an estimator for any cumulative time delays that we might experience when we're sending a packet. Now, sometimes during transmission, we could have a lost packet, and this means that it's a packet that does not reach the destination. And so during the timeout period, if an acknowledgement is not broadcast from the receiver, then the sender will retransmit the packet and then wait for an appropriate acknowledgement to occur. Now, as we mentioned, not only can we have a lost packet, but we can also have a lost acknowledgement. And so in this case, if the sender transmits packet 1, it will wait for the acknowledgement. There is no acknowledgement received, so the sender attempts to retransmit packet 1, and the receiver will recognize that it has received the same packet again, and so it will retransmit its acknowledgement confirming that the packet was received. And so this is important because essentially what it means is that for packet 1, there is going to be a sequence utilized a sequence number utilized to represent the packet. And so the acknowledgement will need to utilize that sequence number to denote that it has received the packet. And so some additional things to consider. How much buffer does the stack need at the sender? How much buffer does the stack need at the receiver? So for the sender, it's going to need just one. And for the receiver, we're going to just need one. So how do I know at the receiver that a packet I'm getting is not a duplicate? We know this because we include an appropriate sequence number. And so we want to say, how big should a sequence number be? And really the sequence number might only need to be 1 bit if there's only one message in flight. And so some assumptions that we want to keep in mind is that in our stop and wait protocol, we can make some assumptions, and that includes packet loss is possible. Packets don't get reordered or arbitrarily delayed. So we can get away with a 1 bit sequence number. However, there are a few fundamental assumptions in a packet switch network that we have to consider, and that is going to be packet loss is possible, packets may be reordered or arbitrarily delayed, and packets may be damaged in transit. So these additional assumptions mean that a 1 bit sequence number isn't going to hold up on the internet. So we use monotonically increasing sequence numbers. And so let's consider the flow of data from our sender to our acknowledgement for various packets. So with packet 0, we're sending to the receiver, it gets received, and the receiver sends the acknowledgement 0. Packet 1 is transmitted, The receiver transmits the acknowledge 1, and packet 2 is transmitted, and the receiver sends acknowledgement 2. And this goes on so forth for however many packets need to be transmitted. And so you want to keep in mind latency. If the latency from source to destination is 240 milliseconds, our round trip is 240 milliseconds. And so we can do 4 packets per second throughput. And so let's consider another approach for transport, and that is going to be the pipeline protocol. The stop and wait protocol provides us a mechanism that is simple, but with the pipeline protocol, we can simply blast packets one after another for transmission and allow for those packets to propagate through the system. In order to allow those to propagate through the system to allow for transmission of multiple packets. What could go wrong here is that we don't have a confirmation of the packets because we are pipelining with no acknowledgements. However, what we can do is a reliable pipeline approach. And with a reliable pipeline approach, we consider that sometimes all of the packets don't make it to the destination, but we have a method for keeping track of those packets. And so what we do is we declare a window where we're going to send a group of packets, and then we'll also be waiting for acknowledgements to occur. And as we start receiving acknowledgements, we'll then start transmitting the next window. And so in this approach, we'll have a window that represents the number of packets that will be transmitted at once. So in this case, we can see that it is 4 packets that are being transmitted. Once we start receiving the acknowledgement, then we can continue with our transmission. So as one packet is received, we can transmit the next packet. So acknowledgement 0 is received, and then we proceed with packet 4 being transmitted. And while packet 4 is being transmitted, we receive acknowledgement 1, so then we can go ahead and send packet 5. So in this approach, we're able to get 4 packets every 240 milliseconds, which is 16 packets per second. And so with our approach for our reliable pipeline protocol, we'll keep in consideration that we'll have buffers at the sender and buffers at the receiving end. And so the buffers at the receiving end represent the acknowledgement. And the size of the buffers are going to be represented as the number of packets that we're going to be able to receive. So for a 4 packet window, we'll need 4 buffers for the sender and receiver. And so if we were to consider what might a packet look like, it can be represented as a structure where we'll have our different components utilized, which include destination address, source address, number of packets, sequence number, packet size, as well as checksum. And so the concerns that we talked about with the transport layer include arbitrary message size, out of order delivery, packet loss, bit errors, and queuing delays as well. And so how can we address these? So for big segments, we use multiple packets. For out of order delivery, we can make use of our sequence numbers. For packet loss, we can use our positive acknowledge checks and buffers. For bit errors, we can do a checksum for the packet. And then queuing delays. We have not discussed how to handle this. So how can we handle this? Queuing delays are going to be a result of network congestion. And so we can have our access networks that are utilized to access a regional network. And so networks tend to grow as more and more users are added. And this can result in some congestion. And that means that the network connections get overcommitted because you have more and more users that are simply being added. And so packets are queued, but they don't get put onto the network, so they are dropped. But because of the sequence number, we can ignore heavily delayed packets if they ever make it. And so in order to account for these type of delays and ensure reliable transmission, we can utilize what's essentially called a sliding window for our packets. And so we have packets sent and acknowledged represented as green. And then we have orange to represent packets sent but not yet acknowledged. And then red are packets that are in the active window that can be sent without waiting for any further acknowledgements. And then for white, we have packets that cannot yet be sent since they are outside of the active window. And so this window size can restrict the rate of packets that are sent. And in turn, it can prevent the buildup of queues in the routers. And so that helps to reduce the possible network traffic or queuing delays that could occur. And so essentially, we've discussed the basics of TCP for the IPv4 protocol. So some things that we've considered with regards to TCP and UDP. TCP is going to be connection-oriented, self-regulating, and data flow as a stream. It supports windowing and acknowledgements. UDP is connectionless, unregulated, message as a datagram, no acknowledgements and no windows. And then we talked about some of the applications and components that are used for transport protocols, whether TCP and UDP. The applications, of course, have included web browser, email clients, instant messaging, video over internet, file transfers, network file services, and remote terminal access as well. So this provides with an overview of understanding the transport protocol and how it operates in IPv4.